Good morning, everyone. Today, we are going to explore one of the most fundamental numerical methods in computational fluid dynamics, the FTCS scheme, forward time central space. So, FTCS is the simplest explicit method for time-dependent partial differential equations, and it beautifully illustrates the core challenges of CFD, the stability, accuracy, and the physical nature of the equation. So by the end of this lecture, you will have derived the method yourself, analyzed its stability using von Neumann analysis, and understood why it works for diffusion but fails catastrophically for advection. So let us begin. We will focus on two prototype equations that represent the two fundamental physical processes in the fluid flow. The first is the heat equation, also called as a diffusion equation, represented over here as partial u over partial of t equals to alpha partial square u over partial of x square. So u could be any temperature or concentration, while alpha is the thermal diffusivity. So this is a parabolic partial differential equation, and it describes how sharp gradients smooth out over time. The second one is the linear advection equation, which can be written as partial u over partial of t plus c partial u over partial of x equals to 0. Now here the c is a constant wave speed. This is actually a parabolic partial differential equation, and it describes the transport of a shape without change. Think of a river carrying a leaf downstream. So in real fluids, we have both effects together in the Navier-Stokes equation. By studying FTCS on these two simplified equations, we learn how to handle each effect numerically. Now, to solve these equations on a computer, we discretize the space and time. We introduce a grid as xj equals to j times delta of x, where j is ranging from 0 up till n of x, while t raised to the power n equals to n times delta t, and in which n is any number from 0 to 1 and up till so on. So the numerical approximation of u at a grid point j comma n is denoted as u subscript j with a superscript n. Now we need to replace the derivatives with algebraic approximations using Taylor series. So we expand uj raised to the power n plus 1 around uj raised to the power n. So it can be represented as this particular equation as displayed, and solving for the time derivative we can find the final equation, which is first order accurate. Now moving on to the central difference in space, we for the first spatial derivative, we expand u at j plus 1 at the time level n, and u j minus 1 at the time level n. So we can write both of the equations as displayed, and subtracting the two eliminates the even derivatives from it. So if we subtract uj plus 1 raised to the power n and uj minus 1 at the same time level n, so we can see over here that the even derivatives eliminate from this equation. So we are left with the final equation as partial u over partial of x at any grid point j at any point in the time n equals to this particular equation on the right, which is representing that it is a second order accurate equation. Now, for the second derivative, we add the two expansions, and solving it, we also got the second order accurate final equation. So these approximations form the building blocks of the forward in time and central in space FTCS scheme. Now, moving on to the FTCS for the heat equation, we now apply the FTCS to a heat equation. We replace the time derivatives with forward difference and second spatial derivative with central difference. So, a discretizing process begins over here, as we can see, starting from the very basic equation partial u over partial of t equals to alpha partial square u over partial of x square at any point j comma n. We substitute the equivalent FTE over here. So ignoring the errors, we solve for u at any grid point j and time level n plus 1. So and we define the diffusion number over here as d equals to alpha delta t over delta of x square. then the scheme would become as uj raised to the power n plus 1 equals to uj raised to the power n plus d, which here is the diffusion number, bracket uj plus 1 raised to the power n minus 2 uj raised to the power n plus uj minus 1 raised to the power n. So this particular equation is explicit. Each new value is computed from three known neighbors. So physically, the term d bracket uj plus 1 minus 2 uj plus uj minus 1 represents the net diffusive flux into the cell. So, to understand when this scheme is stable, we perform a von Neumann stability analysis. The idea is to decompose the solution into Fourier modes and examine whether each mode grows or decays. So assume a solution of the form as displayed, that uj raised to the power n. We assume that it's equal to u raised to the power n times e raised to the power iota kj into delta of x, where k is here the wave number and iota is equal to under root of minus 1, which we already know. So the amplification factor G is defined by u at any time level n plus 1 equals to g times u raised to the power n. So if this amplification factor, modulus of this amplification factor is less than equal to 1 for all k wave numbers, so the scheme would be stable. But if the modulus of this amplification factor is greater than 1 for any wave number k, that mode grows and causes the instability. Now, moving on and plugging the Fourier mode into the FTCS scheme and dividing both of the sides by the equivalent expression, we can simplify using the trigonometry identity as well, and recalling that e raised to the power I theta plus e raised to the power minus I theta equals to 2 cos of theta. And similarly, we also know by the identity that cos of theta minus 1 equals to minus 2 sine square theta by 2, which is a half angle identity. So we can get the final relationship of the amplification factor as g equals to 1 minus 4d sine square of k delta x by 2, where over here is the diffusion number, as we have already seen previously. Now, um, for the stability condition, since sine square is between 0 and 1, the minimum of the amplification factor occurs when the sine square is equal to 1. So g minimum would be equal to 1 minus 4 times the d. We require the modulus of the amplification factor to be less than equal to 1 for all wave numbers. So for positive d, the worst case is the negative g. So we need 1 minus 4d to be greater than equal to minus 1, which gives us that 4d is less than equal to 2, and which gives the d as less than equal to half. Thus, the FTCS for a heat equation is stable if and only if d is less than equal to half in value. So if we exceed this, the mode with the shortest wavelength k delta x would be equal to pi will grow in amplitude every time step, causing oscillations and eventual blow up. Now we apply the same logic to the linear advection equation. Advection equation can be seen over here as partial u over partial of t plus c partial u over partial of x equals to 0. Now using the forward in time and central in space for the first derivative, we can write the finite difference equation from this particular PDE as represented, and solving for uj raised to the power n plus 1, we can find the final relationship in which we can define the current number equals to c delta t by delta of x, and putting it into the earlier equation, we can get the final form, which states that this particular scheme is also explicit. So at the first glance, it seems symmetric and might not be expected to work, but we must analyze its stability. So moving on to for the von Neumann stability and analysis for the advection scheme that we are discussing. So we perform the von Neumann stability analysis again, inserting the Fourier mode as uj raised to the power n equals to u unit vector times ikj delta x into the advection scheme and dividing it by the by this particular expression, so we can simplify and get the final magnitude of the amplification factor as g equals to 1 minus c over 2 iota sine kx k into delta x, and so the magnitude squared of this amplification factor would be equal to 1 plus c square sine square of k times delta x. Now stability amplification lies for any c value not equal to 0 and any k such that sine of k delta x is not equal to 0. We would have the modulus of amplification factor squared would be always greater than 1. So therefore, the modulus of the amplification factor would be greater than 1 for almost all wave numbers. This means that all Fourier modes grow with time. So this scheme is unconditionally unstable no matter how small you make delta t and hence c. There will always be growing oscillations. So this is the famous forward in time, central in space instability for advection. The central difference fails to respect the direction of information propagation, leading to a growth of high frequency errors. Now, coming towards that, why does this happen physically? In advection, uh, the information travels along the characteristics. For c greater than 0, the value at uj raised to the power n plus 1 time level should depend only on the values to the left, that is the upstream. Now, our FTCS scheme uses both left and right neighbors equally. This upfront violation creates a numerical method that tries to pull the information from downstream, which is physically incorrect. So the result is that this scheme introduces a negative dissipation, anti-diffusion that amplifies short waves. This is confirmed by the amplification factor magnitude exceeding 1. So even when the scheme is stable, we still need to understand how it distorts the solution. There are two main types of the numerical errors. One is the dissipation and the second one is the dispersion. Uh, dis- Dissipation refers to the damping of wave amplitudes. If the modulus of the amplification factor is less than 1, the scheme is dissipative. High frequency modes decay artificially. This can be beneficial for stability but smears sharp gradients. While on the other hand, dispersion refers to errors in the wave speed in the exact advection equation. All waves travel at the speed c. In numerical scheme, the phase speed depends on the wave number. Different wavelengths travel at different speeds, causing the shape to distort. For FTCS advection, scheme, the G is complex. G, which is the amplification factor, is very complex. So the phase shift per time step is phi equals to ARG time bracket G. So the numerical phase speed is given by C numerical equals to phi divided by k times delta t. Since the amplification factor is equal to 1 minus iota c sine of k delta of x, so we can compute the phi as equal to arc tangent minus c sine k delta of x. Then we can compute the final form, and using the earlier c equals to c delta t by delta of x relationship, we can calculate the final relationship as displayed over here. So for which implies that for very small k delta of x, arc tangent of x is approximately equal to x. So numerical c would be equal to c. But for large k delta of x short waves, c numerical is much smaller than the c itself. This explains why the sharp corners of a square wave which contains high wave numbers lag behind. So this scheme is dispersive. Now another powerful tool is the modified equation method. Here we ask what PDE does our numerical scheme actually solve. including the leading truncation errors. So for FTCS advection, we substitute the Taylor series expansions back into the scheme and retain the higher order terms. After some algebra, one finds that the scheme approximates as this particular equation written on this slide. So the right hand side is the dispersive term, which is the third derivative, which actually causes the oscillations. Now the coefficient 1 minus c square shows that c is always less than 1, so this is dispersion. And for c value greater than 1, the sign flips, leading to even worse behavior. For the heat equation, the modified equation reveals an additional dissipation term, which is why FTCS is stable for diffusion when d is always less than equal to half. Now, moving on to our part 5, which is the fixes and extensions, in which we would be discussing about the Lex Friedrichs scheme. Because FTCS is unstable for advection, researchers developed modifications. One of the earliest is the Lex Friedrich scheme, which was developed in 1954. So the idea is to replace the u at grid point j and time level n in the time derivative with the average of its neighbors. So uh, the scheme becomes as this particular equation. So this is the uh, equivalent of FTCS plus an extra dissipation term. Performing the von Neumann analysis gives the amplification factor as G equals to cos of k delta x minus iota c sine of k delta of x. So then the modulus squared of this amplification factor would give us a cos square of k delta of x plus c square sine square k delta of x. So the stability would require that modulus of this amplification factor would be less than equal to 1, obviously. So which holds for the modulus of c always less than equal to 1. So the Lex Friedrichs is conditionally stable, but it introduces significant numerical diffusion, smearing sharp features. So now a more accurate fix is the Lex Wendroff scheme, which was developed in 1960. It achieves the second order accuracy in both space and time by using a Taylor expansion. Now, moving on to its derivation, we start with the Taylor series in time, which we can see from these equations. So from the advection equation, we can substitute partial u or partial of t equals to minus c partial u or partial of x. For the second derivative, we can write the equation likewise in this particular slide, and now substitute these into the Taylor series. We can get the equivalent finite difference equation, and by replacing the spatial derivatives over here with the central derivatives and plugging it and using this c value, which is the Corner number equals to c delta t over delta of x, we can get the final form, which is the Lex Wendroff scheme. So it is stable for the modulus of C less than equal to 1 and much less dissipative than the Lex Friedrichs, though it can still produce oscillations near sharp gradients. Uh, Now, nonlinear extension of the FTCS is the Burger's equation. Real fluid dynamics is obviously nonlinear, and the simplest model that captures the nonlinear convection is the Burger's equation. Burger's equation is basically partial u over partial of t plus u partial u over partial of x equal to 0. So this equation is actually the inviscid Burger's equation. It can be written in the conservative form as displayed partial u over partial of t plus partial over partial of x u square over 2 equals to 0. So by applying the FTCS in conservative form would give us the final FDE, finite difference equation of this PDE. Now, this scheme inherits the same instability as the linear advection case, but now the instability is even more severe because the local wave speed u varies. Near shocks, the gradient steepens, and the scheme inevitably blows up unless we add the artificial viscosity or use a more sophisticated method. Now we add a diffusion term over here to stabilize this. We can see there is a new term which is a small artificial viscosity in this relationship. So in this equation, now this is exactly the form of the heat equation we studied earlier combined with the nonlinear advection. So this simple approach is the basis of many shock capturing methods. Now, let us summarize what we have learned up till now. And we have, in the first part, we saw the FTCS scheme for diffusion equation. We analyzed the von Neumann analysis stability using the von Neumann analysis, giving us the amplification factor of G equals to 1 minus 4d sine square k delta of x divided by 2, which requires a stability when d equals to or less than half in value. The second, we discussed at advection scheme using the FTCS scheme, so which was unconditionally unstable. This is why we never use FTCS for convection. Third is the error types. We saw the dissipation damping and dispersion corresponding to the phase speed errors. The modified equation reveals the leading error terms. Then we saw the fixes, which were through two different techniques. The Lex Friedrichs, which added dissipation, and it was stable for the modulus of C value of less than equal to 1. But on the other hand, the Lex Wendroff technique was a second order accurate, and it was stable for the modulus of C value less than equal to 1. Now, nonlinear flows, we use the Burger's equation, which shows the need for artificial viscosity on more advanced schemes. Now, the journey from FTCS, forward in time and central in space, to Lex Wendroff and beyond illustrates the core principles of CFD. We must respect the physics of the equation, understand the stability of our discretization, and carefully manage the numerical errors. Every commercial CFD code today incorporates these lessons: the Corot number, the stability limits, the upwinding, and the artificial viscosity, all trace back to the analysis we just performed today. So I will be now open for the floor for questions. We Thank you for watching.